Hi everyone, welcome to this mini lesson on solving systems of equations. This is a great short video if the original lesson maybe seemed a little bit confusing to you or if you need a nice little refresher. All right, so before we begin, let's kind of review the three methods for solving systems. The first method is by graphing. Now, graphing is a nice way to visually see what's happening with the two or more functions that are showing up in the system. Now, remember, keep in mind when we talk about a system of equations, it can be a system of any type of equation. They don't necessarily have to be straight lines. We can have multiple equations. They can be 2 of them, 3 of them, 4 of them. We can have 100 of them that we're comparing and seeing if they ever intersect. So graphing is a really nice way to visually see where the lines meet or they intersect. Okay. The second method that we really discussed was substitution. Now, substitution is nice because really all you're doing is looking for equations that have one of the variables isolated. So if you're given an equation that has x or y already singled out, then all you can do is now plug that expression into that second equation. The third and final method is elimination. This is probably the trickiest for many students. Elimination requires you to first line up each variable, all the x's lined up, all the y's lined up, all of your constants lined up. In other words, put them all in standard form. And then you're really looking to see if you can create matching coefficients. If you're able to create opposite coefficients, right, 5 and -5, or -1 and +1, that's to make it really easy to eliminate one of your variables and making it nice and clear to solve for the other variable. So now that we kind of reviewed the three different methods, let's get into our first example. Before we do, definitely for today's mini lesson, you're going to want a piece of scrap paper, preferably graph paper if you're able. If not, just take out a piece of lined paper. You will need a pencil, a ruler, and just make sure that you have Desmos Calculator on hand. All right, so let's first talk about how we can solve by graphing. Graphing by hand is definitely time consuming, but once again, it gives us a nice visual of what's happening with both of the functions. Now in this case, we're only looking at a system of 2 equations and specifically linear equations. So I look at both of these equations and I notice, oh, what's very nice about this is that they're in slope-intercept form. So for the sake of this problem, I am going to use 2 different colors to graph. I'm going to use red for the first line, and let's use blue for the second line. All right. You don't need to use 2 different colors. I like to just make it easier in the videos. So for y equals -3x plus 4, I know that this is in slope-intercept form, and the nice information that we can pull out is the slope and the y-intercept. So I'm going to start by plotting my y-intercept, which is +4. And then I'm now going to count up and over to identify the slope of -3. So down 3, 1, 2, 3, over 1. Down 3, 1, 2, 3, over 1. Down 3, 1, 2, 3. And as I do this on my paper, you can do it on yours. And I typically always overplot lines, especially when I'm doing it on the computer, because it just makes it a little bit more accurate. All right, so I've created this line. Now we're going to go ahead and plot the blue line. Y equals 3x minus 2, so I'm going to plot my y-intercept of -2, and I'm going to count up and over. 1, 2, 3, over 1. I always like to try to find the point of intersection with my slope, if possible. All right, create a ruler, draw that straight line. All right, now we're going to visually look to see where the 2 lines intersect, and we can see clearly here, this is where they intersect. I'm going to zoom in, and it's at point 1, 1. So my solution to this system is 1, 1, or 1, 1. It's the ordered pair. Now keep in mind, we do make errors sometimes. So a very nice, easy way of checking your answer is to always plug in that 1, 1 to each equation. Don't forget, when we're looking for a solution to a system, we're looking for the only point that satisfies both equations. So although there's infinitely many points on this yellow line, or what I'm highlighting in yellow, and there's infinitely many points on what I'm highlighting in orange, the only point that satisfies both equations is the point of intersection. So in theory, use some quick mental math, plug in 1, 1. If x is 1, this becomes -3 plus 4, which gives me 1 for y, which is perfect. In the bottom equation, always checking both, 3 times 1 is 3, minus 2 does equal 1. So we know that since it satisfies both equations, we have the correct answer. All right, so let's move on. The other method of using to solve by graphing is to really use Desmos Calculator, and this is a nice, easy way of getting your final answer. So over here, we notice we have a system. I forgot the curly braces, so I apologize. So what I'm going to do is I'm going to open up Desmos Calculator, and as I do that, I would like you to pause the video, go ahead and open up Desmos Calculator, and go ahead and plug in both of these equations and see if you can identify the solution using the graphing calculator. All right, so I'm going to open up Desmos, and we're going to see here, let me zoom out. Negative 4x minus 15y equals negative 17, and negative x plus 5y equals negative 13. The red graph is shown, the blue graph is shown, and then what we can do to figure out the solution is just use your mouse to tap the point of intersection, and we have 8, negative 1. So I'm going to go back over here, and my solution here is 8, negative 1. Now I can't take a screenshot using my iPad, but if you're able to do that on assignments, go for it. Now once again, always check your answer. Take that time to plug in 8, negative 1 into each of the equations and see if that holds true. All right, let's move on to substitution. Now, solving by substitution is a nice method, especially if you have one of your equations where a variable is already isolated. So I'm going to zoom in on number 1. Go ahead and take a moment to write this down on your piece of scrap paper. And as you do, I want you to think about which equation has a variable that's already isolated. Excellent. We should see that y equals 5x minus 7 has your y already isolated. So every time I see y, I'm going to replace it with 5x minus 7. So my second equation, I'm going to take my second equation, negative 3x minus 2y, and I'm going to start to write that down, but once I see that y, I'm going to replace it with that expression 5x minus 7. It's like saying let y equal 5x minus 7. Now I have an equation that lends itself to solve for x. So I'm going to use what we know about distributing. Distribute that negative 2. I'm going to combine like terms. Negative 3x minus 10x gives me negative 13x plus 14 equals negative 12. Next thing, we're going to subtract 14 on both sides. All right, and we got negative 13x is equal to negative 26. We get my final answer of x equals 2. Now I'm not quite done yet. Although we have our x coordinate, we still need our y coordinate. So now I'm going to look back into my original equation, and I'm going to look to see which one makes more sense. Should I plug in x into my first equation, or should I plug it into my second equation? And for me personally, it really doesn't matter, but if we're looking at efficiency, I'm going to plug it into my first equation. If I replace x with 2, we're going to see that y is equal to 10 minus 7, which is 3. Now we have an x coordinate, which is 2, and my y coordinate 3, and what we're saying here is that this is the solution to that system. This is the only value of x and y that will satisfy both equations, and this is the point of intersection. All right, let's go ahead and try number 2, same idea here. We're going to start off by looking at both equations. We're going to ask ourselves which equation has one of my variables isolated. Once again, y equals negative 2. And we're going to use that and plug it in or substitute it into my second equation. So I have 4x minus 3 times negative 2 is equal to 18. And you don't need to use different colors. I'm just doing it there just to really color coordinate. So 4x minus 3 times negative 2 gives you positive 6 is equal to 18. I'm going to subtract 6 on both sides. I'm left with 4x equals 12, x equals 3. A lot of times students just make computation errors, so just be careful as you're solving them out. From here, we have two different options. We can move back to my original equation, and I'm going to ask myself, which one can I plug it into? Well, you're going to notice I cannot plug it into my first equation, so I have to plug it into my second. So 4 times 3 minus 3y is equal to 18. That's going to help me solve for y. 12 minus 3y is equal to 18. Negative 3y is equal to 6. Y is equal to negative 2. Now, many of you guys might say, well, Ms. Coot, we already see that y is equal to negative 2. You're absolutely right. I personally like to always take that extra step. If this came out to be a number other than negative 2, then we know we did something wrong. So my final answer is 3, negative 2. Once again, we can check our work by plugging in 3 for x negative 2 for y into both equations, which in this case is the second equation, and see if it holds true. All right, so for both of these examples, we used the method of substitution. We were able to see that both of these lines do in fact intersect, and the solution indicated the point that satisfies both equations, or the point of intersection. So go ahead and copy down number 3 and number 4, and I'd like you to pause the video and try both of these problems out. You're going to try your best to use substitution. Now what makes both of these difficult is you're going to notice that neither of these equations have a variable isolated. How cruel of me. So in each of these examples, what I'd recommend you do is to identify which one of the equations would actually lend itself to substitute a variable easily. So for instance, in number 3, this one would probably be the easier one to solve for y. Go ahead and pause the video when you're ready, unpause it, and we'll reveal the answer. All right, at this point, hopefully you've solved both of these problems out like TV magic. Let's look at number 3 and number 4. If you need to, you can pause the video to dissect your work compared to mine, and my final answer are shown there. For number 3, you should have gotten a solution of negative 3, negative 2. In number 4, you should have gotten a solution of 3, 2. How'd you do? Awesome. Let's keep moving. The last and final examples we're going to look at are solving by elimination. Now, elimination is a little bit trickier. All right. There are some helpful steps here for solving by elimination. In the simplest of words, though, we do want to make sure that they're written, both equations are written in standard form, and we're really going to look to see if we can determine any opposite coefficients. So I'm going to zoom in on this first example here, and I notice my x's are lined up, as well as my y's. And I'm purposely using the signs too, and my constants. And I look to see if any of these variables, x's and y's, have opposite coefficients. And in this case, we notice that they do. Negative 6x and positive 6x. So I'm going to rewrite this problem like a giant addition problem. Now, we don't know how to solve equations with two variables, so we have to eliminate one of the variables. So I'm going to start all the way to the left, and I notice negative 6x plus 6x gives me 0, so that cancels out. I'm going to move to my next column. 5y plus 4y gives me 9y, which is equal to, go to the third column, y minus 10 gives me negative 9. So my final answer here is y equals negative 1. Once we have one of the variables, then we can go back and plug this in into either the first or the second equation. So for here, it does not matter. I'm just going to use the first equation, negative 6x plus 5 times negative 1 equals 1. It doesn't matter which equation you use. X equals negative 1. So my final solution here to this problem is my x is negative 1, my y is negative 1. So my final solution is negative 1, negative 1. That's the only value that'll satisfy both equations, and it is the point of intersection. So that was a little bit of an easier elimination. Let's look at it a little bit harder. So over here we have negative 6x plus 6y equals 6, negative 6x plus 3y equals negative 12. Now I'm just going to highlight what my eyes are looking at. So the first thing I'm going to look are my coefficients to my x's. We've got negative 6 and negative 6. I'm going to look at my coefficients to my y. I have positive 6y and positive 3y. And I don't really need to look at my constants, but I don't want to leave them out, so I'm going to highlight them. Now I look here, and I've got a lot of different options. In theory, I could try to make this coefficient negative 6 by multiplying every term in that second equation by negative 2. Another way, which I would actually prefer to do, is I wish that one of these equations had a positive 6. So it does not matter which method you go to. So your work may look very different than mine. It may look very different than your peers, but you have to choose a method. So in this case, I'm going to choose to turn this negative 6x into positive 6x. To do that, I'm going to first take a look at my original system. I'm just copying down the original system. I'm going to ask myself, what do I need to do to get this negative 6x to turn into positive 6x? Remember, because the whole goal is to cancel those out. And in order to cancel my x's out, I need to have opposite coefficients. So in order to cancel out, correct, I have to multiply that by -1. But I can't just magically multiply that by -1. I need to multiply every term by -1. Now keep in mind, if you do it like this is not showing your work properly. To keep this equation true, I need to multiply every single term by -1. Excuse me. So, actually I don't need that equal sign. Let's rewrite each of these equations after multiplying that second one by -1. So we have -6x plus 6y equals 6. The next equation will be 6x minus 3y equals 12. We're going to treat this like a giant addition problem now. All right. And now I have -6x plus 6x, that cancels out. Now I'm going to look at my next column. 6y minus 3y gives me 3y, excellent, equals 18. Y is equal to 6, excellent. Now from here, once again, take this 6, plug it into either of my original equations. Not any of the other ones, always into the original. It does not matter which one I plug it into. I'm going to choose just the first one. So if you have -6x plus 6 times 6 equals 6, lots of 6's here. -6x plus 36 equals 6. I'm going to subtract 36 on both sides. We've got -6x equals -30. X is equal to 5, which means my solution is 5, 6. What this means is that these lines intersect at the point 5, 6. It also means that it's the only point in the whole world that'll satisfy both equations. All right, so we just looked at 2 examples for elimination. Now it's your chance to try them out. So go ahead and pause the video, try number 3 and number 4 out, really trying to play out which would be the most efficient strategy to eliminate one of my variables. All right, at this point, hopefully you've done number 3 and number 4. Like TV magic, number 3, your answer should be 9, 5, and number 4, your solution should be 4, -2. Now, as you check your work, you might notice that my work or my strategy might be very different than yours. So if you have an incorrect answer, you're going to want to make sure that you really distributed with the negative correctly. That's the major error I typically see with elimination. All right, so in this video, we talked about how to solve by graphing, solve by substitution, and solve by elimination. All 3 strategies are really wonderful ways of solving for a system of equations. In this unit, we really will be focusing on systems of linear equations, but keep in mind, remember, systems can be systems of any types of functions or equations. Hope this video helped. Thank you so much for watching.